So hello everyone, my name is Andrei. I work on a Compose team, kind of really internals, compiler runtime, lazy stuff, and many, many more things. And today I want to talk to you about performance. So this was some kind of focus for us in lazy layout specifically. We learned some lessons from there, and we kind of figuring out some guidelines, generic guidelines for Compose right now, internal as well. So I'm kind of wanted to share some of those things that we figure out with you here. So let's start. The first thing about Compose, when it just came out, we were striving for is correctness. So we wanted to figure out how to catch up to views, to Vue framework, especially with the 10, 15-year old framework that was already packing a lot of functionalities. It was really hard to kind of implement all of that. And right now, we're a much better place than we were a year ago. And that's why we're switching a lot of our focus to performance. We already wrote a lot of components. We already wrote a lot of things. We know how Compose performs. In certain situations, how we use Compose primitives that we created initially. And it turns out we actually use them in a completely different way that we initially intended to, which is one of the ways where you encounter some of the edge cases where Compose doesn't perform well. So we're focusing, doing kind of a lot of focus there. But performance of Compose in most of the cases is kind of in a good place. But there are a lot of edge cases that some people are facing into, and that's what we're going to talk about today. And lazy layout, specifically the focus of the talk here, it's kind of a bit of debating you to come in, because they're benchmarking all of Compose. Each time you implement a lazy layout, you put something in there, you kind of get all of this content. You have to put in a lazy layout. You get it during scroll, which is happens immediately. It should happen not noticeable to the user, and that's why it's really important to make sure that the content in lazy layout is performance specifically. And there's also a lot of comparison with the recycle view, and we are always tracking performance on the lazy layout that way, because it was one of the first things that came out to us. So the talk was initially mostly about them, but then I figured out you don't really care about we found two allocations in this list, and we removed them. That's really sad talk. So for people who actually want to improve performance of Compose in their own applications. That's why I kind of switched the topic a little bit. Actually, we'll try to talk about tips that will be useful to you, developers that are implementing their own components and want to make sure they're performant inside lazy layouts and other ways. So first things first, I was politely asked to add a little bit of the disclaimer in the preamble to this presentation. It's the first thing is you don't need to optimize unless you need to. So you find a few places in your app that are actually slow, but otherwise you don't really actually have to proactively try to improve the performance of all of your elements. Just write the composable elements that you're comfortable with supporting, that you feel a natural for Compose. And only when you see that some frames are missing or there are some kind of performance, try to optimize them. And when you're optimizing things, you're obviously going to measure them, benchmark in some kind of way. And there are these three things that I'm always kind of noticing before, trying to do before I actually run my benchmarks. I measure in release mode, not debuggable, then I enable array, and I use precompiled binaries and a baseline profiles. And I wanted to talk about what kind of slowdown you got to expect from each of those things. So for example, if you measure, here we go. For example, if you measure in the release mode, you get 2x speed up compared to debuggable. And the reason for that, not only in some kind of magic APK stuff that Android runtime does, but also in the Compose itself. Because Compose serves a lot of source information that is relevant for UI inspection and some kind of some other stuff that we use internally in the runtime to help you debug stuff. But at the same time, we also use live literals right now. And live literals is this kind of thing where you have a constant, and you could just switch to Android Studio. Android Studio would propagate the change to Compose and just replace it. And it worked in a way that we just replace all the constants with states. And we're going to talk about states a bit later. But that was slow, because we were boxing these constants. We were constantly trying to remember where the states would treat and all of that. So that kind of was a 2x split down in my experience. I just measured all of the numbers in today's presentation. I just measured it before on my local device. So they're a bit anecdotal, but this is they align with the general perception that we saw in the different benchmarks that we run more rigorously. So similar things with array. This is pretty simple. You have bytecode, you optimize it, you get faster bytecode in return. It's less classes to load, it's like faster execution in general, less dead code, and so on. And the last thing is a bit more tricky. We haven't seen this before Compose, but it's related to like how Android runtime optimizes binaries. So before, we were optimizing the bytecode for views in the framework itself. So you just depend on Android jar. Android jar is already optimized for you. Here, we kind of bundle all of the Compose runtime into your application. And it turns out that by default, your application runs in kind of like slow mode, which is like interpreter mode. And then it kind of gets compiled over time, or like ahead of time, by the Google Play or whatever distribution you're using to be faster. And that's what like precompiled binaries here are. So baseline profiles help to that. They help to prepare those like machine code for your application ahead of time. And if you don't do it, you get like this type of thing in your profiles for your traces or benchmarks. And what you see here is like runtime trying to optimize your application as it goes. And this is obviously really problematic. It's like a constant GC activities in the background. It's like some of those things, like we compile a bit of the bytecode, we figure out like what's the machine code for that, like what's optimized part, and then we stop the world, we replace it with the new thing, and we continue. So this is obviously pretty slow, 2x slowdown in my experience in general in benchmarks. You want to avoid all of that, so make sure you follow these guidelines if you measure performance, if you try to figure out what's wrong with your app. So as we're done with that, let's actually talk about how we can, what we can do with the Compose code to improve our performance. And every time I'm thinking about like how to make slow code go faster, I think about these 3 tips that one of my colleagues from React Native, Ruben Norte, given me like 2 or 3 years ago when I was starting with performance for the first time. So the first thing that you can do with this piece of the slow code is just not execute it, or execute it less. This is kind of optimization that is related to caching it smartly, making sure that you don't run this piece of code all the time, or make sure in Compose case you're not invalidating composition all the time, like don't have that many recompositions or other things. Oh, sorry. The second thing is do it faster. So this is like usual CS stuff. Beta algorithm, maybe somebody wrote a bubble sort for some reason. You just replace it with the normal array sort or list sort, whatever it is in the standard library for Kotlin, and it goes faster and that stuff. Similar, like you use hash map instead of list for searching for items or something like that. It's obviously going to be faster as well. And the last thing is doing some other time. We mostly use it inside of Compose, so there is like not a practical tips that you can use for that. But it's mostly related to doing some things in the other thread, doing something smartly on the same thread, but later. So if you're familiar with how like lazy list prefetching works, for example, it tries to kind of predict what items is going to be shown on a screen next, and just fetches it if there is some idle time in the frame or something like that. So this is like basically 3 tips that I try to follow when I'm thinking about how I can optimize something in my piece of the slow code. And we're going to go through some of them on a bit better examples with composition in particular, and the ones that we use with the lazy layouts. So the first thing is, how do we not do certain stuff, like not execute slow code in Compose? So for that, let's talk about what composition is. Composition is basically a tree. It's a tree of groups that kind of map your execution of your app. So for example, here we have a composable function app, which has a parameter show text. So for that, composition is going to create a group. It's going to remember the parameter, and this parameter is going to be used later if you restart it. Also, we just compare those values in the slots. So I will call whatever the green thing is a group, and whatever the blue thing is slot. Basically, each group has multiple slots in there, and they kind of coordinate it together. Then you can memorize the values directly there. So you can just like put something, like remember something, it's going to be put in the slot, in this group, and memorize of this particular place in the code execution path. Actually, thinking about this, remember works a bit differently right now because it creates a different group, but we're going to optimize it sooner to be closer to this. And after that, you can also call a composable function. So composable functions, each call of the composable function, whenever you enter a new composable function, going to create a new group. It's going to be different kinds of group depending on like it's an inline function, if it's stable or not, and so on. But in general, you create a group, you memorize some parameters for that, maybe it has remembers inside of it and so on, and that continues all the way down to the layout node. So layout node is the result of the composition. It's basically UI tree we're trying to build. Similarly, you could have like some different code execution paths. So for example, you could have if-else condition in there, and if you try to compose it with true, you get like group for if, group for box, layout, and layout node in there. But if you replace it with else, we remove that group completely, starting from like the root where the group execution changed, because like it's completely different group from the compose perspective. And we just replace it with else. From that, we create a layout node tree. And that layout node tree can now be measured, laid out, and drawn. This is free passes that we're doing later, unrelated to composition. So one thing that I noticed, like many people that start with Compose specifically, but many advanced developers also do, they think about composition as like the only place they can update stuff, the only thing they can invalidate stuff. It's not exactly true, because each of the measure, layout, and draw passes, they are also kind of invalidatable scope. So if you read something, like read some state in those modifiers, or like other things that you use for invalidating state in composition, you'll get similar kind of update that composition does, but for much smaller scope. So for example, this is a slide from my presentation from DroidCon London, if you've been there, but this is basically, we have a box, we put some state in there, and we put some modifier size in there, and we control it by state. So we can just invalidate the state, change it, and change the side of the box. And this is pretty inefficient because like we read it in composition, whenever we change the state, we're gonna invalidate the composition pass for this particular case. And it's gonna do a lot of work while we could just invalidate the layout or measure. So here are like two examples. You can read it inside the measure if you want to change the size of the composable, but if the state would have respect like to the position of the layout in particular, you could read it inside the layout block and validate even smaller scope. And similar thing happens with draw. If you like, for example, use like background color modifier or something like that, and you specify the value in composition without like the lambda modifier that we have there, it's gonna do kind of the same. And I measured this thing on like my low-end device. So we usually try to measure performance of Compose on really slow devices. This particular device is 10 times as slow as a Pixel 7. And for this small composition, it's just like a box with a state. You saw it yourself. It's 3 times faster to just invalidate it and measure. With draw, you get like 10x improvements. And practically what you miss in there is like a lot of things. Sorry, I missed the point with this arrow. It's like too beautiful. In any case, what I wanted to say is that you're missing a lot of performance by just invalidating composition instead of invalidating like smaller parts in here. And this composition is really simple. You have like 1 millisecond that takes to just invalidate the box, but it would be like more complicated stuff. Probably you don't have just boxes in your app, right? You have like more complicated things in there. If you invalidate that, you obviously get like much better, well, probably much worse performance out of composition and much better performance out of measure. So it will like just 10x going from composition to measure and so on. But you know about derived state as well, right? Derived state is kind of made for fixing those things. And when I was starting with Compose, I was using like derived state quite a lot, and it actually helps. Like here, if we invalidate only derived state and not composition as a whole, we get similar performance to what we get out of measure. We don't execute anything in the composition. We just like check if the value is the same. Yes, it is the same. We're good. But the problem with that is like many people are using derived state incorrectly. And we saw many examples over the years how that affected that, including in the lazy layouts as well. So the first thing, when you start with derived state, I saw some people just wrap any access with state to that and just like, okay, derived state doing some caching probably is going to cache. The thing is that this is a really simple example. It could be way more complicated, obviously. But you have like a state which has like an integer, and each time the state changes, you want to compute the derived state of that. which is like just the state multiplied by 2. And obviously, each time the state changes, the state multiplied by 2 also will change. And that means that derived state just doesn't do anything, it doesn't do any caching, and it's just like some extra cost of maintaining derived state and some other things. Similar thing happens when you just use derived states to get rid of the lint warning that we introduced. When you use the first visible index in composition to do it, it changes on every scroll. People just write it with derived state of. Warning goes away, but performance problem doesn't. You still scroll, you get like recomposition on everything because derived state now gets invalidated every frame, but the result of derived state is also gets invalidated on every frame. What you can do instead is compare it to 0, for example, or whatever you're trying to do with that. But if you compare it to 0, like in this example, you get like true or false, depending if item is 0 or not. So it's like way less frequent way of invalidating it than with just using it as previously. Some other things I noticed is sometimes derived states are used with the items that don't implement equals, for example. So you just have whenever the state updates, for example, here layout info visible items updates every frame. And it doesn't implement equals for obvious reasons that even if it did, the offsets will be different, so we just like decided not to. But here you get invalidation on every frame as well because visible items are different each time. What you want to do is probably map it to some kind of comparable values instead and make sure that they are consistent between scrolls of whatever the change that you're trying to detect. For example, like maybe a list of visible indices is already a better example because like they don't change on every scroll. Or maybe there is some kind of more meaningful things that you're trying to extract from this layout info. And the last thing is probably the most complicated thing of the tips of the derived state is the nested derived states. So when you use them, like nested is like you access one state inside the other, you probably expect that if the first state invalidates, the second first state invalidates and is like has the same value, the second is not going to be invalidated. So by default, that's not the case. If you want that behavior, you need to specify the equality policy. And obviously, like if you access that state in composition or measure, that's not going to be the case because both composition and measure has like implicit structural equality policy applied to that. But nesting derived states, they don't. And the reason for that is backwards compatibility because we introduced it like a year ago or something like that. So if you nest derived states or you think your derived state will be used in a nested way, use the equality policy on your derived states. And the last thing I wanted to talk about is like the access cost of the state. Because, well, it's something that we don't really think about and we use state sparingly. So this is a table that maybe some of you have seen before. It's latency numbers of like access from the memory, disk, and network. It's kind of a ballpark things. Maybe they're outdated a little bit now. It's like how many years ago it was introduced. But the reason for those numbers, like you don't have to know them exactly, but you have to know like ballpark of what's the difference, like what's the difference in the order of magnitudes between those values. So I computed a similar table for the composed stuff. So first you have the local variable breed. It's kind of 1 nanosecond, but I don't know exactly because the benchmark only measures with the 5 nanosecond precision, unfortunately. So then fields read is 5 nanoseconds or less. Not sure exactly, but that's what my precision was. And then we have method call. In particular, here is like virtual interface method call, which is also a bit slower because of the interaction. Synchronous read, that makes sense. We lock something, we unlock something. And then you have map get, which is just like doing some kind of more interaction, looking up the hashes and so on. So here comes reading state value and derived state value. Those particular values are way lower if you don't read in the composition, but I included the reads in composition because that's where we read those states usually. Well, it's composition and measure. Numbers are pretty close there. And as you can see here, it's like 20x difference from the map get. It's like way slower than synchronized read. And the reason for that, we're actually doing a lot of map get sets, updates, and so on behind the scenes to make sure that your states and derived states are tracked correctly, corresponding to the correct scope, and making sure that it's just like recorded and updated later whenever you changed it. And this results in a different cases like this. Like you just have a measure, which takes a lot of time, but when you check like what actually happens in there, you just read the derived state all the time. For example, this particular case was from the lazy layout like with the 10 or 15 items, we were reading 2 derived states per each item, and that caused like 60% of cost of just like the whole measure, just reading these derived states repeatedly. So obviously we don't want to do that. Just coercing it to a single derived state read on the start and just like reading that value instead improved our performance quite significantly on the cases when we didn't have to subcompose. So from all that I mentioned today, you'll be like, oh, derived states are bad while we even using that, just remove them from runtime. And they're not. Like as you saw from the like initial graphs, we have like really good performance if we invalidate them correctly. The problem is like some people don't. It's really sometimes hard to understand what's invalidated correctly, what's not. So the moral of the story here is to probably try to figure out like if your derived state actually does something in your app when you use it. And maybe sometimes when you see something like that where derived state doesn't do anything, just replace it with a simple value access. It's going to do the same time with like 5,000 nanoseconds safe on your low-end device. All right, so this is the first section over, but now I'm going to talk about modifier node. And this is like a grand example of doing something faster, like algorithmically faster, by just replacing one algorithm with another one. And the story of the modifier node starts with modifier composed. So modifier composed was kind of this abstraction that was created to make sure that modifiers can have state that is unique for each layout node. So and they achieved that using composition. As you can see, it's just a bunch of remembers, and those remembers were used whenever you propagate for node. So how it works is just like you have a modifier, you had a modifier, you create it once, and then you can just repeatedly propagate it to each of the layouts. And they will all create like their own instances of that modifier clickable with each own unique state, ripples, and so on. But the problem comes when you start to kind of update those things, because they're not skippable. You just create a lambda, which not comparable by default. The composition that it creates also returns a value, which is not skippable by default. And you get a lot of problems with that, a lot of performance problems. So for example, if you remember like box with something, like composition of the box with something was taken like 1 millisecond, so just like composing one modifier clickable was taking 1 millisecond. And the reason for that is basically this. It's like we created a lot of things in composition there. Like clickable modifier was actually composed of way more smaller modifiers related to focus, maybe some kind of indication like ripples and so on. And that presented with a lot of problems that we wanted to solve. So the solution for that was the modifier node, and it consists of 2 parts. First is this modifier element. Modifier element is a simple comparable object, kind of like a descriptor of this modifier. And as it's comparable, we can just, again, chain them as we used to modifiers before. And as we chain them, we can compare these chains between each other. And for example, if we see that this chain just doesn't matter, like if the chain is kind of the same as it was in the previous iteration, we can just make sure that we skip those updates. Whenever a modifier element gets to a layout node, and layout node is not initialized yet, we create modifier node out of that. And modifier.node is a different beast that we didn't have before. It's basically a stateful object, kind of like a mini view. And it can launch different coroutines that will be scoped to lifecycle with particular modifier. Whenever you remove modifier, this coroutine scope will be canceled. And it has like attach, detach, lifecycle, and also reset. We will talk about reset a bit later. But and we have different types of modifier nodes. You have like layout, you have draw, you have measure. So those things can be used to implement basically everything that we used to implement with the usual modifiers, but without API changes. And the interesting part comes when we actually get to update those modifiers. Because we can just compare these 2 chains of modifier elements that we had previously and we have now, check like which nodes we need to create, detach, attach the new ones, and then just update the values if we need to. And update is really simple. So before, if we have like different modifier clickable with a different lambda, we had to go through separate hoops in the composition to kind of go update the lambda, relaunch the pointer input, and so on. Here we just like update the lambda value, and that's it. Or like for padding, we could just like update the value of the whatever padding we want, and invalidate layout for that particular layer. And it's similar with the background as well. We just invalidate draw for that. So it's like really incremental, really fast updates. And this is the comparison of some of those things. So for example, modifier clickable, the example that we used before, went from like almost 1 millisecond for composition layout to draw to 0.5. And it became as fast as fill max width. Fill max width is like simplest modifier you can find. Probably like modifier size or something like that, which is similar complexity. And even like fill max width became faster when we migrated to modifier node. And when we thought that probably not only modifiers could be migrated to this thing, actually like composables also have some kind of intermediate state sometimes that we propagate to layout, like measure policy or layout nodes themselves. So probably those could be also represented as a modifier nodes. So we migrate text, and you can see like there are some meaningful like 20% performance improvements there as well. And we also saw different like bigger numbers on faster devices. It really depends on the version of Android you're using and how fast the device is. This device is like really, really slow. And yeah, there is also like some anecdotal evidence that we had like 50% less overtime frames, like junky frames in some of the Google apps with that as well. So the moral of the story here, if you have something like modifier composed, where you remember a bunch of stuff in a composed modifier, propagate it to a layout node, inflate it, and create something complex, or you have like some kind of complicated composition that you want to maybe convert to more stateful lifecycle related object, you can use something like that. Just create an element for that, create a node, and like migrate your modifier to a bit more reusable and recyclable state. Right now, we don't have a lot of guidance related to modifier node, unfortunately, but we'll be publishing soon with the 1.5 release because that's where our modifier node is actually stable and ready to use for your modifiers as well. And the last thing I want to talk about is lazy layout reuse. So lazy layout reuse is kind of similar to what RecycleView does with its own views. Whenever you have like some kind of composition, it's not composition in use, it's like some kind of values, you bind them, you unbind them, but reuse the views from the previous view holder pattern. And to describe that better, I'm going to come back to the composition case that we had before. So composition is like a solid block of groups, usually, but there's like one layout that defies those expectations. And this is a subcomposed layout. I think this currently is the only one. And what it does, it creates like small piece of the composition in your regular path, and then it during measure, it can synchronously create more elements. And this is obviously use of LazyColumn, which just like takes those composition and creates one element per each of the items, or creates composition per each of the items. So they kind of correspond to what you see on the screen usually between the device stuff. Like all of them are different compositions. And whenever we scroll, we obviously have like one element just went out of screen. We don't have to present it anymore. And probably we could reuse it. That would make sense from like just algorithmic standpoint. And the problem with the lazy reuse in particular is the effect. Because like sometimes we subscribe to some kind of data flow, or maybe we like launch a video or something in this element, and we want to make sure that those things are disposed correctly. And the problem with disposing, we want to make sure that people just use whatever elements they have already, like disposable effect, launched effects, and some other things for doing these things, instead of like thinking, okay, so I'll be using this element only in usual composition. I can use disposable effect here, but here is like a special case for the LazyColumn, and I'm doing like reusable disposable effect or something like that here. So this is like obviously not really fun and really hard to support from like component library perspective. So we opted to do is like all of those effects are implemented as a remember observer. We can just clear up those remember observers in there and just clear out all the data that we have associated with composition, but keep the structure there. And that was pretty all right. We also started reusing the nodes, and that was like 10% improvement, but it's still pretty slow. So as modifier node came along in like 1.4, we also started using modifiers. And what we're doing here, we just like reset the data in the layout, but in the composition, but we also reset the modifiers as well. That's what on-reset callback that I referenced before is for. So you have some data, stateful data in the modifier, we call and reset on it, and it's just clears up and prepares it to receive the new data later on, like unsubscribes or certain things. And that's given us the 20 to 30 faster composition and create, and then 50 less allocations on average, which kind of transforms into even faster create on some devices that are a bit worse with the GC. And it also started reusing Android too, because we introduced certain lifecycle events that made it really hard without them to reuse Android too before, but now we have them, and we can also reuse those things. So if you have video players, maps, or something like that, Andrew Bailey implemented reuse of Android starting from 1.4 review. It's like separate overload of Android view with the onReset callback in there. So that's kind of it for me here. I just wanted to round up the things that we talk about today and see what we can take out of this talk. So first is like cost of state. State is not free. If you use state, you invalidate a lot. You also pay the cost of accessing the state and remember, like recording those reads in certain blocks. You also want to make sure to use derived state carefully, and yeah, know about the access cost as well. With modifier nodes, with the 1.5 release, I recommend to look into that if you have like custom composed modifiers, something like complex enough, and consider also moving like complicated lifecycle related composition logic into those modifiers as well, because it could be reused in it could have been reused in the lazy layout whenever we use it. And the last thing is kind of, there is a certain way you can optimize for reuse in lazy layout. Obviously, you already know about content types and other things, but you also want to make sure in the single content type that you preserve your composition structure. So you have a similar code path followed by both of those components with like if-else's kind of matching, otherwise layout nodes and modifiers won't be reused there. And yeah, you can reuse views now, assuming like they match the code path and composition is ready to reuse those things. So where are we going next with all of that? Obviously, it's all pretty good, but it's far from like ideal situation there. We still have a lot of work to do on our side. We still continue with the migration to modifier node. We right now migrated 60% of our modifiers, but we obviously could do better on that. We're also working on the compiler optimizations. As you saw on my slides, we have the composition which kind of creates box layout nodes, and all of those things are kind of wasteful in many senses. We create really tall and narrow compositions that we could optimize further. We could also optimize remembers, as I did on my slides already. We're updating runtime to make sure that state reads faster on average, and they kind of do the same functionality with reads now that we have the framework and we know how those states are used inside modifier nodes and inside composition as well. And we're also rewriting some core pieces of composition as well, like slot table. We optimize it for performance of the actual composables that we see in the wild. And the last item here is we're still trying to figure out if we could reuse some items in the lazy layout better than we do right now, because obviously we still discard a lot of composition, and composition cost, as you saw on the slides, is really large compared to like some other things that we do. So obviously, like this is all the small subset of the future work. I'm just talking it from my perspective. There are a lot of things that also happen behind the scenes that I don't have that much visibility into. So that's why the star is there. All right, this is all for me. Do we have questions? We have like 10 minutes for that, I believe.